Your phone, laptop, and even washing machine use this circuit. Today, we'll be building the foundation of digital logic, a D flip-flop, and verifying it works in simulation. Welcome to the world of digital design. This is Metastable. A D flip-flop is one of the simplest units we can program on an FPGA. All modern FPGAs come built with D flip-flops, and depending on the device, there can be anywhere from thousands to even millions available for programming. So with all that, what is a D flip-flop? A D flip-flop is effectively a 1-bit memory storage. It takes in a 1-bit input, which can either be 1 or 0, and returns the input as the output after a small delay, the input line being called D and the output line being called Q. Now, in order to get the flop to work correctly, we also need to add a digital clock input. The clock is an oscillating signal that constantly switches between 1, high, and 0, low, and allows us to synchronize our data. Digital clocks work like a metronome and allow for harmony in digital systems. A full clock cycle consists of both a high and low state. When the clock transitions from low to high, the flop samples whatever value is present on D and updates Q almost instantly. Even though Q changes right away, the rest of the system won't use that new value until the next transition or clock edge, because all the other flip-flops also wait for the next transition to capture their inputs. Now, in addition to this, the basic D flip-flop has an output Q0, which is always the opposite of Q. So if Q is 1, Q0 would be equal to 0, and vice versa. I should note that Xilinx FPGA architecture doesn't implement Q0 lines for inverse operations, so we won't be adding it in our coding example. So what's the point of using D flip-flops? Even though they're only 1 bit, we can use them to delay or pipeline our design. Imagine we have 2 signals that are inputs to our design. One is ready immediately, while the other passes through a set of logical operations, which causes it to lag and need pipelining in order to pass FPGA timing requirements. If we present them together as is, we'll run into synchronization errors. But if we pass the quicker signal through a D flip-flop, it will be delayed and line up with the slower signal. In addition to that, we can chain D flip-flops together to form registers and store larger values. With an understanding of a D flip-flop, we're ready to build one in VHDL. The next thing we need to understand is the components that make up a VHDL file. In VHDL, every design that we create will have 2 major components, an entity and an architecture. The entity of our module acts like a black box. The only things that are visible from the entity are the input and output of our design. All the inputs and outputs are contained in a section called the port list. We can use this port list to either connect to external hardware or other VHDL signals and entities. The architecture contains the actual logic of our module. In the architecture section, we can implement processes, instantiate other VHDL designs, generate code blocks, and connect signals however we like. We're now ready to start writing VHDL code. For this, you'll need some kind of code editor. I personally use VS Code. You can find a download link in the description of this video for it. I would highly recommend downloading a VHDL extension, as it'll make working with VHDL much easier. I've found modern VHDL to be a pretty useful extension. In VS Code, the first thing we'll do is create a VHDL file. We'll name it dff.vhd. DFF for D flip-flop, and .vhd being the file extension for VHDL files. Now the first step in creating our design is adding the IEEE library. IEEE, the Institute of Electrical and Electronic Engineers, is an engineering organization that develops protocol standards. If you've ever used Wi-Fi or Ethernet, you've used IEEE standards. IEEE also standardized VHDL in 1987. We need the IEEE library because VHDL's native bit type is too limited. It only allows our signals to be either 0 or 1. Real hardware isn't that ideal. Signals can be unknown, uninitialized, or in high impedance states. To model this, we use standard logic, a more versatile 1-bit type defined in the IEEE package Standard Logic 1164. Standard logic can represent 9 states: 0, 1, X or unknown, U, uninitialized, Z, high impedance, W, weak unknown, L, weak low, H, weak high, and dash, don't care. We'll learn more about these states in future videos, but we'll end up working with the first 4 states listed for the majority of the time. Adding a VHDL package is similar to adding a header file in C++. We can add the package by writing use IEEE.standardlogic1164.all. Every VHDL compiler should have the full IEEE library built in, even though it's technically not native to the language. With the standard logic type added, we can start writing the entity. First, we write the keyword entity, then the entity's name, which in this case is DFF, followed by the keyword is. Next, we create our port list. We can create it by using the keyword port and using parentheses to wrap around all of our ports. Here, we list all the ports going in and out of our design. For our design specifically, we have 2 inputs, our clock, and our data, D, and 1 output, Q. The syntax here for ports is that we list the port name, a colon, the direction of the port, in or out, and then the data type followed by a semicolon, unless it's the last port. For example, our clock can be written clock, in, standard logic, semicolon. Now we'll do the same for the other ports. We can then write end entity, followed by a semicolon. From here, we'll move on to the architecture. To start the architecture, we'll use the keyword architecture, followed by the type of architecture we will be using. You can name the architecture type whatever you want, but it's a good rule of thumb to give it a name that resembles what you're doing. In this particular case, we are writing synthesizable code, or code that can be run on hardware. So we'll call our architecture RTL. RTL stands for Register Transfer Level. RTL describes on a register level how our data flows through the system. Just like for the entity, we give the architecture a name, DFF. I want to note that it's good practice to name both the entity and architecture after the name of your file. Next, we type the keyword begin. This keyword separates 2 major regions within the architecture. Everything above begin is the declarative space, where we can define things like signals or custom data types, which we'll go over later. Everything after begin is the design logic, where all statements run concurrently or at the same time. For this specific design, we don't have anything to declare. One of the most important features of VHDL is the assignment operator. Unlike most programming languages, VHDL uses these symbols for assignment. At first, this can be confusing since these symbols look like a less than or equal to comparison, but in VHDL, it's used to represent the direction of the assignment. Now we know that for a D flip-flop, Q is assigned to the value of D. So couldn't we just write Q is assigned to D here? We could, but the problem is that this assignment happens without any clocking. That means Q will always be equal to D, because in concurrent logic, the assignment is made continuously. This effectively creates a wire between Q and D, making them identical, which is not quite what we want. For a D flip-flop, D should only be sampled when the clock transitions from 0 to 1. To achieve this, we need to use something called a process. In an architecture, all statements in the design logic run indefinitely, but a process allows us to run through a section of code only once when triggered. We can control the activation with a sensitivity list, which is a list of ports and signals that if any change, the process is executed. In our case, we'll just put in the clock, so that whenever the clock status changes, the process runs. Processes, like architectures, use the keyword begin. We don't have anything to declare in the process, so we'll move on to the design logic. Now, the sensitivity list will trigger the process when clock transitions from 0 to 1 or 1 to 0. We only want D assigned to Q during the 0 to 1 or rising edge transition. So we'll use a conditional statement to make sure that we only make the assignment when we want. Here we'll write if, and then use the built-in function rising edge of the clock, then. Now we can finally write Q is assigned to D, and we can end the conditional with an end if. This is also the end of the process in architecture, so we'll write end process and end architecture. Now if we've wired everything up correctly, on the rising edge of the clock, D is assigned to Q, with Q's new value being available to the rest of the system on the next rising edge. But with that, you've written your first piece of synthesizable code. The next step is to compile our code to make sure that we haven't made any mistakes. We can compile the code by running it in ModelSim. There will be a download link for ModelSim in the description. One thing to keep in mind is that the Intel website says that the software QuestaSim is replacing ModelSim. I downloaded the starter edition for QuestaSim but ran into a bunch of licensing problems. Let me know in the comments if you get the same issue. If this happens to you, ModelSim still works completely for what we're doing. QuestaSim just has current support and some additional verification tools. When you open ModelSim or QuestaSim, you should see a layout similar to mine. Now to compile our code, we simply click on the Compile in the Compile tab at the top, and then select the files we would like to run, and then click the Compile button. After running, we can see that it compiles with 0 errors or warnings. So our code compiles, meaning that it doesn't have any syntax errors or illegal statements. But how do we know that the design is working as expected? We could try to simulate our current design, but we would have no data to give our system, so we wouldn't learn anything. What we need to do is create a test bench, which will allow us to send dummy data to our design to show us the behavior of the system. A test bench is a virtual environment we can use to verify design functionality. Our test bench will be written in VHDL and will look similar to our synthesizable code. There are, however, some things we can do in simulation that we can't do on hardware. I'll address these differences as they come up. Now let's create our test bench file. Let's name it dff_tb.vhd or dflipflop testbench. Just like the dflipflop file, we need to add the IEEE library and standard logic 1164 package. From here, we create our entity dff_tb. Unlike our design entity, we are not going to add any ports. Everything happens inside the test bench, so we don't need to worry about receiving data or sending data out of the test bench. Now our architecture type will be TB for test bench to show it's a simulation file and not a synthesizable design. Because we'll be running a simulation, we need to declare some items. We're going to declare what are called signals. Signals act like ports, but are completely internal to the architecture. They can act as either registers for values or wires connecting ports. In this case, we will be creating signals identical to our original design's ports. The way we create signals is first by using the keyword signal, followed by our signal name, a colon, and then the data type. One cool thing we can do is give our signals initial values. We will want to do this for our inputs. We can set initial values by adding :equals, and then our value. In this case, we will want clock and D to start at 0. This is how we write 0 for the standard logic type. Now we can move to our simulation design logic. The first thing we want to do is set up a clock. We can do this by writing clock is not clock after 5 nanoseconds. Basically, this means that after 5 nanoseconds, we set the clock to the inverse value. If the clock is 0, it will become 1, and vice versa. So the clock is high for 5 nanoseconds and low for 5 nanoseconds, which gives us a total period of 10 nanoseconds. If we use the frequency formula where f is equal to frequency and t is equal to the period, we get a clock frequency of 100 megahertz. This means our clock would cycle through a high and low state 100 million times a second if it was on actual hardware. It's important to note that the keyword after is only usable in simulation, but with that, we have our clock signal set up. To test our design, we need to create an instance of the design we'd like to test. We can do this by writing dff entity work.dff, where dff is our instance name and work.dff is a reference to our design. Work here refers to our project library. Any files that we create will use the work prefix. From here, we add a port map, which we can use to drive the original design's ports with our signals. Connecting the signals to the D flip-flop ports will allow us to manipulate the inputs and see the result take place in the flip-flop. To map our ports, we use the VHDL assignment operator but in the other direction. So to map the clock signal we created to the clock port of the D flip-flop, we would write clock is driven by the clock. We will do this for all the ports on the original design. The last port that is assigned does not have a comma at the end. This might seem a bit confusing since we now have a set of signals and ports that are named the exact same thing, but it works the same way as using an appliance like a lamp. A lamp has 3 lines: hot, neutral, and ground. If the lamp is unplugged, it may or may not work, but we have no way of testing it. Only when we connect the lamp's electrical lines, hot, neutral, and ground, into the corresponding wall sockets can we verify that the lamp is actually working. Now we still have one input to account for, our D input. If we ran the simulation as is, both D and Q would stay at 0 forever, since we set D to 0 with the initial condition, which isn't helpful. To manipulate D, we're going to use a process. For our Testbench process, we don't need a sensitivity list since the process is simulated. Now we can write wait for 20 nanoseconds, and then D is assigned to 1. This means after 20 nanoseconds in the simulation, D will be set to 1. Wait is another one of those keywords that can only be used in simulation. From here, we'll wait for 80 nanoseconds and set D to 0. After all this, we will type wait by itself to effectively end the process because not having a sensitivity list means the process will repeat endlessly. An important note here is that the 3 items we have, a clock assignment, an entity instance, and a process can be in any order. The architecture, whether synthesizable or not, runs all statements in parallel. Now we can run our simulation. We first need to go back to ModelSim and compile both our design and Testbench. Once these both pass, we can run it in simulation. To run the simulation, we need to click on the Simulate button at the top of the window. From here, we open up our work folder and select our design that we'd like to test. With our simulation open, we can add our signals to a wavetable to see the values of our design in simulated time. We can add our signals by highlighting the ones we want and clicking Ctrl+W. From here, we will type in that we want to run our simulation for 1000 nanoseconds. We can get a full zoom by clicking the magnifying glass icon or by pressing F. We can zoom out by using the minus magnifier button here or pressing O. And we can zoom in by using the magnifier or pressing I. Let's see how our design did. It looks like it's working. Our clock continuously goes from high to low with the correct period. D is 0 until 20 nanoseconds, and then 1 until 100 nanoseconds, or 80 nanoseconds later. Our Q value starts uninitialized until our design generates an output. From the simulation, we can see that Q mirrors D with 1 clock cycle of delay. Now, this isn't exactly how hardware works. The simulation uses something called delta time. In reality, D would be assigned to Q almost instantly, but because the data isn't accessed until the next clock edge, it still gives an accurate system response. But with all that, we have a working design. That's all for this video. In the next one, we'll be creating an LED light show and implementing the design onto hardware. Leave a like if you enjoyed the video and subscribe to stay up to date. See you in the next one.